Okay, you got a data with a basic dimension.
Are you locking us here?
Yeah, let me. So here we have our datum defined. So A is the back, right?
Yeah.
Okay.
A, that's the back of this. C is the left side. B is the bottom. And right now, we're kind of ignoring this. We're just talking about this whole. So the dimensions look like they're coming from the datum up. So they're coming from the datum over. And then we're dimensioning it, the size, and then we're doing our call out for position. So because this has a position tolerance, we don't want a tolerance on these numbers.
So that's why
we make them basic, right?
Yeah.
So now our position tolerance for this hole is the center has to be within a cylindrical tolerance zone of, what's that number?
0.25.
25 thousandths. Right? So you go to the last place, that's thousandths, it's 25. It's 25 thousandths. And you see the last 3 frames for the datum reference are empty. So it doesn't matter the order that we put these A, B, and C in.
because you're not using
Then why put
They
one
haven't
there?
been defined yet.
Yeah, they're defined. A is the back. Or
The order isn't, but it doesn't always go A, B, C.
that's what I'm asking you.
Yeah, it should.
Do these go A, B, C? Does the order of them matter?
I think logically it would.
Yeah, the order matters. What's important about it?
B and C.
That there are no defined tolerances.
There's a defined tolerance right there.
There's standard. There's
No,
standard
there's-
tolerance.
No, that's our tolerance.
It's just saying that B,
No,
C,
that's
and A is not being.
Yes, but the three, because we can put up to 3 datum references in here. What's the importance of being first, second, or third on the list?
The whole not dimension from
I don't-
So, what does that mean?
A. B and C are more important than
So, what are these talking about? What is the datum? That's a reference plane we're going to measure from, right?
Correct.
Or we're going to use it to line up when we measure.
So it'd be B, C, and A?
And so what it is the way that these work is you have the primary, the secondary, and the tertiary. So the primary datum reference, the first one,
Is the
is
main-
going to line up with 3 points of contact on that datum plane.
Right.
The second one, you're going to line up with 2 points of reference. The third one is going to be 1 point of reference. And so, make it a little bit smaller. So if it's ABC, that means that the back, when we go to measure it, we're going to lay it down on the back of it until we get 3 points of reference. So until it stops rocking, that'll be 3 points. Then we'll slide it down till it's B at 2 points, and then slide it over to C. So we put it down on A till it stops rocking, go to B, slide over to C. And then we can measure these 2 dimensions. To find that, this plus sign is the center location. And so that part probably passed, right? So we measure over here, we measure up, find the perfect location, compare it to the actual, and check it. So if it passes, it's good. If it doesn't pass, it's bad.
Totally not.
If we change that order to ACB, now we lay it down on the back until it stops rocking. Slide it over to C till it hits in 2 points, and slide it down to B. Now look at where that is.
Oh, it changes
You can see down here, that gap there,
Mhm.
because of hitting the 2 points here. Now it's kind of turned a little bit. Will that part pass?
Sure.
If the tolerance is 0.025 and that's an inch and a quarter,
Yeah.
Yeah.
really, from there to there is less than 25 thousandths of an inch.
Well, if it is, it'll pass.
So
The whole inch and a quarter?
what do you, for the distance from
Oh.
B to the hole is an inch and a quarter. So that means that diameter of that circle is about a quarter of an inch. So that's all the way at the bottom. That's probably like an eighth of an inch away from the center, right?
125.
Is that less than 25 thousandths? So that's probably a bad part, right?
Yeah.
But it's the same exact part as this. Same exact part, right?
It's not a position.
Here it passes, here it doesn't pass.
Because of the order of the way you went. made
Just
it
because of
all-
how it's aligned and because of the order of our datum references. So with GD&T, we can define the order based on what's important, how it's actually going to line up in the assembly. And this is going to ensure that it's checked the same exact way every time. Because if we didn't have GD&T, someone's just going to check it by measuring it, maybe not lining up against a jig or anything, and that it could pass by one person, it could fail by another person. But by GD&T, now it's either going to always pass or it's going to always fail no matter who does the measurement. Does that make sense?
Yeah.
So with GD&T, we usually will have some kind of a jig to check it. So it's no longer just measuring it with calipers. So you have to line it up so that you can measure it. So the next thing we'll talk about is virtual condition. And so this is the worst case size of the part that we can still meet the tolerance and size measurements. So a pin, it's the size at its maximum material condition plus the tolerance equals the virtual condition. The hole, that's maximum minus their virtual condition. So that's the maximum material condition. That's basically when the hole, or the pin is the biggest and the hole is the smallest, right? Right? Pin is big, hole is small. See the virtual condition of each, and that's going to be the worst case scenario. Same thing here, when kind of the opposite. Now it's the pin when it's the smallest, the hole when it's the biggest. Then that difference is the most amount of space there'll be between the two things, right? So big pin, little hole, that's the worst case. Big or little pin, big hole, kind of the best case, but that's also the sloppiest, right? So that could be the worst case, right?
You have more space than you have.
If you got more space, you got more slop,
Little pin.
things aren't going to line up quite as nice.
Or move too much.
We have this, and we add some GD&T to it.
So the maximum is 1,000.
So now we've got our GD&T added. If we look at this, we can see that the diameter tolerance zone, what the tolerance is. There. And then that's at it when it's at max material condition. So this hole here, this kind of red piece, that's the smallest that hole could be when it's perfectly aligned. So that's kind of, if they had a pin there, that pin would always have to go through, right? So they could test it by making a pin that it's at the virtual condition. Right there, having 3 points. And here you've got just kind of 3 little stands on the primary datum. But that's not what we did on the last example, right? Here, it's just a flat plane on the back. Here they've actually got 3 specific points that they're measuring from. And so those could be called out on the drawing as datum targets, exactly where those are and dimension to where they want those pins to be put. And then they put that on. If it fits, you know, it's a good part. So, remember I told you the material condition gives us some extra stuff? Remember, as the hole gets bigger, it doesn't have to be lined up perfectly anymore, right? So that's called the bonus tolerance. So anytime we have a maximum material condition or a least material condition, what we do is we can create a chart of our tolerance, so kind of our limits of our tolerance, so minimum size, the maximum size, and because this is a maximum material condition on a hole, it's going to be at the small size of our tolerance. So that's maximum material condition, right? So here we have our tolerance, 1/1000. It's still here. And our bonus tolerance, at MC, we have 0 bonus tolerance. If we get bigger, so we're moving away from maximum material condition, we get the same amount of space that we move away as a bonus tolerance. So this one is 1/1000 bigger, we get 1/1000 bonus tolerance. That one's 3/1000 bigger, we get 3/1000 bonus tolerance. 4/1000 bonus tolerance. So we can just add those together and get our total tolerance. So when the hole is at its maximum material condition, it has to be within 1/1000 of the perfect center. So the diameter of the zone is 1/1000. If we get down here, now the diameter of the zone is not 1/1000, now it's 5/1000. The hole is 5/1000 bigger, it can move around 5/1000. Does that make sense?
Yeah.
It's bigger, it can move around that same amount. Is that, yes?
Yeah. Yeah.
With him and
Easy to understand?
Yeah, that was easy.
So that right there, remember we already got 57% bigger space by making it round instead of square? Mm-hmm. Now, how much more space do we get?
You got 57, you get 0.062,
So
62.
what's the area of it?
3.14?
So 0.001. Times 3.14. So the area of that zone is 3.1, 3/1000 of a square inch, right? That's 15/1000 of a square inch. So 5 times larger tolerance zone because of this now. At least material condition. So now we've got, so that's 500%. So now we're at 557% more tolerance space. Right? That's kind of big.
Yeah.
So better. So how can we make sure we get good parts out of this?
By shrinking your tolerance.
So let's go back and look at there's our center point. That's our tolerance zone. So before, we had that, right?
Yeah.
So we added 57% there. Now what happens if we do it and our center is right there? What do we do? So now we're outside the circle. So that circle is based on maximum material condition. What do we do?
Go further away from the back.
Make the hole bigger.
Right.
So if that's where our center is, we just need to figure out how far away it is.
Make it bigger.
So let's say
Maybe 11.2.
that one gives us a circle right there. So now that would be within that circle.
Be a good part.
So now we just drill our hole out to that size. And then it's a passing part, even with the center being off. Does that make sense?
Yeah.
So now we can aim for making things at least material, or I mean, making my maximum material, or close to maximum material, and if we get off position, we just go more towards least material until we get to the right size to make it work. So now you have parts that instead of being scrapped, now they're just reworked and they're good parts. So we're back here. So this one has a lot of stuff.
Now position.
Let's look at
Position with the perpendicular.
this. Let's look at just that feature control frame right there.
Okay, it says that position is at 0.4 maximum, and B is at maximum too, but not A.
So what is this telling us?
What are we talking about?
So let's
Okay.
let me go back here. Or I should answer it. So what is this telling us? Let's read through it. So
Position
position
is at 0.4
is 0.4
max.
in maximum material condition relative to datum A
And B
and B at maximum.
B at maximum.
So the position of what?
Position of the hole.
What hole?
No, it's position of that part.
No, because this is the tolerance about the hole.
Position of that part. That whole, that back part.
This is the position of what?
Surface?
What surface?
It's no surface mark.
What is this feature control frame referring to?
Center point.
The center plane of what? Of this dimension, right? It's with the dimension, so it's talking about the center plane. Is it that center line right there?
Well, I thought it was, but maybe I'm wrong. Center
No, it's the
plane
center
of
of
the
the
It's
piece
the center plane of the part,
of the object.
which just happens to correspond with that center line of that hole, right?
Yeah.
Which is also the profile
The surface.
Of-
Profile surface.
of the surface. Actually, the profile of the surface is talking about this line here,
Yeah.
so that has nothing to do with that. But this one just happens to correspond to the center line of that hole. But it's not meaning that that is the center line of the hole. Okay?
No, because you got that one on there.
So that's the center line of the part. So the center line of the part has to be in position relative to datum A, which is where?
Datum A is right down there, it's the,
No.
there, those two surfaces, bottom
Yeah.
part.
Datum A is this bottom two surfaces, right? So relative to datum A and datum B, which is what?
B is
Cutout part.
the cutout.
What about the cutout? Where is it? Is
The,
datum B
left
this?
side
No,
line.
it's the left
Well,
side.
actually, it'd be the same, it wouldn't matter, right? Either parallel.
What does that mean?
So it's equal to.
The center, right?
Center line.
Center.
So just like this one is the center of this part, datum B is the center of that notch. So it's showing us the center line of this piece has to be positioned relative to the bottom and the center line of this piece.
That's why they say line up a B,
Okay.
right?
What?
That's why they got the M next to B, because it's still pulling off that same center line of the part.
Just because when this changes, we want to be able to change the tolerance also. So on the last example, we just had the M here. Now they have two M's. Now we're just going to have a bigger table. So now we have the feature driving this M. So the feature sizes that we have possible. And then datum B and its sizes we have possible. So when both the feature and datum B are at least material, or at maximum material, sorry, we have our 0.4 tolerance. I mean our 4.4 tolerance. If either one of them gets bigger, we move away from that and get bonus tolerance. If they're both at least material condition, our tolerance is 1.1 millimeters. So we can go from 0.4 to 1.1. It's kind of a big difference, right?
But that's that's tied into where your feature number is, right? So I mean, the 1.1 is only if the feature's at 38 going up. Is that correct?
Yeah, if the features are the least material and the datum B is at the least material, that's the 1.1.
Right.
If they're both at maximum condition, then it's 0.4. And then based on the table, we can go away from it. So what does that really mean? It means that this is perfect condition, right? That's how it's drawn at maximum condition for 38 and 12. And this one I just picked 38. But that's perfectly lined up, right? The center line of the slot here, center line of the feature, lined up. That's it. At maximum material condition. Now this is at maximum material. That's at maximum material condition. That's at maximum material at the extreme of the tolerance.
See how far it can go.
That's at
At the least.
at least of the feature, but the maximum of the slot. And then I could have made the slot to the least and adjust it. But you can see that the relationship of that hole and the slot are stayed and lined up perfectly, because this hole right here is lined up there. So that's kind of basically the outside is just shifting around the inside stuff. So that's why we can do it. Let's look at another one. What is that?
Positional hole.
So it's
F4.
telling us this hole. Why does it have two different?
Because one's the depth and the other one's the.
Nothing's about depth there.
No, that one is perpendicular to,
That symbol means.
If it was depth, it would have a depth symbol up here.
I thought so because it's through.
no, that's perpendicular.
Well, that's old standard.
Perpendicular.
That means it's going all the way through. If it was depth, the depth symbol would be here.
I mean, that 0.05 is perpendicular to C.
No, that's that one that we saw earlier, and I don't know what it is. I don't know.
So we just basically did something like that, right?
Yeah.
Oh, that's perpendicular to that back wall.
So what this is
that
meaning
back
that
surface.
this hole
It's
has
perpendicular.
both a position tolerance and a perpendicularity tolerance.
Perpendicular.
Why would it have both? Oh, I forgot to mention that the position tolerance,
Just lining up or something.
when you position it like this, there's some perpendicularity to it automatically, because if you're lining it based on that, on the back plane, this hole can't, I mean, it's locked in perpendicular, right? So why are they doing it perpendicular again?
So now it's just been just to see only.
But what's the difference between these two tolerances?
Because one's giving you the amount of space between that perpendicular angle.
And one
Look
top
at the
will
number.
Be least and the
Look at your tolerances.
top will be least and the
Giving you a
bottom
max
will be max.
diameter of 0.5, 0.05.
The numbers.
0.4 and 0.05.
The position is 0.4,
Yeah. And
so it can move around 0.4. And that also tells it that it has to be perpendicular, but only perpendicular within 0.4. What's this one telling us?
500.
Now that it has to be perpendicular within
500.
500ths also. So the position within 0.4 or 0.4, and then perpendicularity is tighter at 500ths.
It's tighter.
So 500ths is smaller than 0.4, right?
So actually, it's going to be 0.45.
No. No, it has to meet both those conditions. It has to be positioned within that, and it has to be perpendicular to that. So, and here I was just talking about that. So, let's actually get in and do one of the samples like for the homework. So for exercises today, we want to take these feature control frames and write out what they mean. Okay. So just write it out verbally what it means. And we'll do one that's a little like what we're going to do right now. We're going to draw it out and then apply the tolerances to it. And then here we got two basic parts. And you're going to make it so that they always fit together with a minimum clearance of 0.005 of an inch. And then it tells you what the tolerance for this surface is. Or no, the tolerance for that surface. So the size tolerance is 0.06 for this. And you have to readjust the sizes to make it fit. So that you always have 0.005 of an inch tolerance. So we'll do one that's kind of like 1013. So, what's the first step? Draw it, right? There you go.
Oh, yeah.
On this part, it gave me a limits tolerance, right? 0.499 to 502. What size did I draw that circle?
0.5.
0.5, right? It's in the middle there. That's our nominal dimension. It's a nice round number that's somewhere in there. I can dimension that and get this tolerance back out, right? So might as well do that. So what's my next step?
Identify datums.
No.
Pointing in the direction from front, top, and right side view.
Do I really need a front, top, and right side view?
I don't see why.
No.
Front and top.
Just because instructions tell you to do something doesn't mean you need to do it. We're thinkers, not copiers.
Well, then I would guess we'd determine
No.
point A.
No.
Oh,
What's the next thing to do?
dimension, the basic,
What do we do before we dimension?
move to model space.
Then you go to our layout, right? So maybe an A. Set a scale. Can I make these fit better on the page?
Yep.
What should I do?
Put them side by side.
Like that?
Well, yes, sort of.
Is that okay?
No, they're not lining up with each other.
Nope, they're not lined up. So what should I do?
Scale them.
Change the size of the paper.
I can do it on A size.
Or
What
C.
should I do?
Section.
What?
Section.
Just say it, Kenny. Just rotate it, right? So you go rotate like that. Now they're still lined up. They fit on the paper a lot better. Now I can make it 1-to-1, no problem.
And what took you so long?
He was moving his phone like that for like 2 minutes. Maybe I want to have a little bit more space. I don't want it to be half. Maybe one's going to get a little crowded, maybe. Maybe not. We'll try it and see. You can always rescale it. Block my viewport. Now what? What should I do now?
Start putting in dimensions. Measuring from point to point.
Determine your datum. No?
No.
Start dimensioning, start mentioning the
Really?
distance of things, the lengths of things, the widths of things.
It's probably something I should do is before I start dimensioning still.
Would you want to set up, feature control frames?
Nope.
Okay, I'm going to start dimensioning. Tell me what I'm doing wrong.
Change layer.
Yeah, I need to change my layer, right? It's easier to change your layer first and then to come back and do it later. Where's my cheat sheet? Where's O? There we go. Where we don't write letters at the end, we use symbols. corresponding 0, 3 places, upper 0.002, lower 0.001. There we go. Right? So, maybe I'll think then. How can I get a nice center line to stick out on past that square?
Going to dimension.
Right?
M center,
Will that make it out there? I don't want to make it out here, right?
huh?
If I do that, it's only going to put the center mark for the circle here.
You can
But if I want it to
beyond
make
the
it
square.
stick out, what?
You can lengthen it beyond the square.
But this circle's small enough, it's only going to